Okay, so I don't know what happened on those other videos, but what I'm going to do now is I'm just going to talk through our notes. So maybe this will help, and it's all going to be in one big run through. So maybe this will help, and I'll get these uploaded, but I'm going to keep the other videos on there, even the ones that are delayed in time. All right, so here's the moral of this story. All of these that you already know, if you haven't memorized them already, you need to do it now. Your reciprocal identities. Now, obviously, cotangent, if you put it on this side, then tangent would be in the denominator, right? Same thing with cosine secant, sine cosecant. All that same thing is happening. For your tangent is sine over cosine, therefore cotangent is cosine over sine. This is a direct relationship with the reciprocals, right? So sine over cosine and cosine over sine are reciprocal, and you know tangent, cotangent are reciprocal. All of these work together. That's the moral of that story. All right? And the Pythagorean identities, know them, love them. You'll find out next semester in calculus that this also has a nice, sweet relationship with derivatives. But for now, just know that this is what's going down. All right? These you have to memorize. You have to know these. All right? Here are some new ones. You do not have to memorize these. These even in odd and identities. Now here's the deal. Sine and cosecant are buddies, right? Cosine secant, tangent cotangent. If I remember back when we were talking about odd and even functions, and if you input a negative value and your output is also the opposite, that's what makes it odd. For tangent, if you input a negative, your output will also be negative. Again, tangent, cotangent are odd. Cosine, if you input a negative, you output the original. Let's go back to our graph that you just had on your test. Sine here, if I'm looking at it, is around 0. So if I swing this around, it is reflecting around the origin. Reflecting around that origin makes for that odd function. Do you remember that? Even here means I have my y-axis symmetry because cosine starts up at 1 and then goes from there. It is reflecting over that y-axis. And if you remember, y-axis symmetry is even functions. Like a parabola, right? Those kinds are all y-axis even functions. And here, and with our polynomials, we could see what was happening because of the exponents. Sine and cosine, you can't see what's happening with the exponent. Same thing with tangent. You put a pin here, and then you swing this around, and it is also reflecting around that origin. All right? You don't have to memorize these. It is good to know that a sine is an odd function and cosine is an even function, but beyond that, we're good. We're good. All right? Now, so here you can just plug these in. If I input a negative for cosine, I know I'm going to output just the regular function because it's even. If I input a negative for sine, I'm going to output the negative because it's odd. There's the moral of that story. That's literally all there is to it. All right. Now, in my math lab, you are going to have problems where you are going to convert into sine and cosine. So all of those identities that you know, you're putting in your toolbox, and in your toolbox, and you work those out. So here is the problem that we're starting with. Tangent plus cotangent. So if I want to put tangent plus cotangent in terms of sine and cosine, tangent becomes sine over cosine. Cotangent becomes cosine over sine. Then anytime you're adding rational expressions here, you have to get a common denominator. With a common denominator, you got to represent. I have both sine and cosine in my denominator. So that means I multiply this left one by sine over sine, because that puts sine and cosine. Whatever you do to the bottom, you have to do to the top, right? That's keeping it even here, because I have sine over sine is the same thing as a 1. Cosine over cosine is the same thing as 1. It keeps it equivalent. I said even, I meant equivalent. Then sine times sine is sine squared. Cosine times cosine is cosine squared, and you have that common denominator. As soon as you have your common denominator, you can put them together in the numerator. So now in my numerator, I have sine squared plus cosine squared. And does that look familiar to you? It should. So now I have my Pythagorean identity. This is, I'm telling you guys, you got to know these. So sine squared plus cosine squared is equivalent to 1. So anytime you see sine squared plus cosine squared, you can replace that with a 1. So I take tangent plus cotangent, and you simplify it all the way down, and you end up with 1 over sine cosine. All right. The whole deal with this 10.1, this 10.1 is a big deal. And it's a big deal not because it's super application based, because it's not. It's really not. It's a big deal because you need to do this manipulation. And so I just put in here, my math lab, I don't like how they do verifying the identities. I don't even at all. So in your homework, you're going to have odd even like at the beginning and changing to sine and cosine like what's happening here. Now I will tell you, verifying identities, it's such a big deal because it's a way of thinking. All right. So what we're getting ready to do is not, oh, let me find multiple ways to apply this, because there aren't. This is not how this works. What this is a way for you to use your mind to problem solve and think through this stuff. That is its purpose. So here are the main trig concepts. The main trig concepts are the unit circle, which we covered. That's a big deal. Verifying trig identities, which is what we're going to do right now. It's going to build problem solving skills and manipulation of trig identities. That is the key. Manipulation of your trig identities, you're going to use a ton in Calc 2. But just verifying this and just building up your problem solving skills. So a lot of people say, when am I ever going to use this? Well, you're not going to use this. Like particular things, you're never going to have to verify trig identities again. That doesn't make sense. It's just getting these trig identities stuck in your head so you know how to manipulate them and how they relate to each other. That is a big deal. And getting your problem solving skills. How can I work with this? All right. And this is what you are not going to find in my math lab homework, because they do not do a good job of it, in my opinion. And you know I got one. So if I verify this identity, you start with this equation to begin with. This is already true. Ah, cool, right? This is already true. Because this is already true, all I'm trying to do is make both sides look the same. That's my goal here. Start with the craziest looking side. So, in my opinion, the one over here on the right looks the craziest. And here's the big deal. You cannot cross the equal sign. You're not trying to solve anything here. You're not trying to find the value of x. You're not solving anything. This is not an equation. This is a verification. All right? And the goal is to try to look ahead. So, if I have cosecant on the outside, I'm going to distribute that. When you distribute your cosecant here, I switched it over here to my 1 over sine, because whenever I distribute that, 1 over sine, it gives me cosine over sine. Then sine on the top and sine on the bottom gives me just this 1. Well, what is cosine over sine? Nailed it, right? And when the sides are equivalent, that's how I know when I'm finished. And that's the ultimate goal. Sometimes you work both sides. Sometimes you just work one, right? So however that works, you just cannot cross over the equal sign. Our whole goal here is to manipulate your trig so that the both sides are equal. That's our goal. All right? Oh, good. See, look at that. Every once in a while I come up with something good. The purpose is the process. This is a proof. I'm just saying this side equals the other side, and I'm proving how that is true. All right? It's just the process. This is just the thinking process. Okay, let's do some more. This is just practice on this, like factoring or anything else. You practice this manipulation, practice manipulation. That's when you get good at it. All right, so let's start here with this. On this setup, I have tangent minus cotangent over sine cosine. Secant squared minus cosecant squared. All right. To me, I'm seeing this cosecant and this cosecant over here on the right and secant on the left. And I know that these are reciprocals. So in my head, what my head is doing is saying, this is 1 over cosine. This is 1 over sine. That puts a cosine and a sine in the denominator. And I got a cosine and a sine in the denominator on the left. So that's what my head is doing. So when I said look ahead, and you're going to just keep writing down each side, because my goal is to make them look the same. If you just get caught up in yourself writing down one side, you're going to miss your goal. I'm not solving for anything, right? I'm making them look the same. So I have to have my goal in front of my face constantly. That's what's happening. So if I change this to cosine over sine, they're squared because my secant and cosecant are squared. Getting that common denominator, multiply those together. Sine squared times 1 minus cosine squared times 1. Getting that common denominator. Then I'm looking at this saying, all right, now I have this cosine squared and this sine squared. All right, sine squared and cosine squared. I've got 2 here on the right and 1 on the left. So this is all in terms of sine and cosine. Well, maybe I ought to make this in terms of sine and cosine and see what plays out. So then I change my tangent and my cotangent to be in terms of sine and cosine. And then I get my common denominator. So sine times sine is sine squared. Cosine times cosine is cosine squared over my common. This is a division bar. So when I divide and you multiply by that reciprocal, because this is looking good, right? All right, that's looking good. Multiply by that reciprocal here. And then we come up with our answer. Sine squared minus cosine squared. Sine squared times cosine squared. Our ultimate goal with these problems is just to go back through and say, okay, how can I make them look the same? Keep your goal, and you can go back and forth. It doesn't matter. Just keep working it. Now, you could have taken this one and then tried to simplify it or make it in terms of secant, cosecant. You could have taken this monomial and divided into each one of these to see what you came out with. Any of that is fine, all right? The process is the proof. The process is the purpose. So whenever I go to grade these, or as you're working through these, there is not one way to do them. As long as you are using your identities, that is the key. There are tons and tons of ways to do these problems. All right, so I want to just, I'm really trying to push that concept of think through it, right? Just think through it. So that may be something to do here. Write this problem down. Here, let me lose this. Write this problem down on your paper and try it yourself if you want. Then you can see what's going on. Here, it's already in terms of sine and cosine. I don't have anything squared, so I can't use a Pythagorean identity. It doesn't really help me in order to change things in terms of secant and cosecant. However, anytime you have a 1 plus or a 1 minus of these sine cosine situations, you can do the conjugate, right? This difference of squares value. Because if I have 1 plus sine and I multiply that by 1 minus sine, that is the square the first term minus square the second term. And all of a sudden, I now have a derivation of my Pythagorean identity. So the Pythagorean identity doesn't always just have to look like this. It's also an equal sign, right? I can manipulate that and move it around to whatever works best. And in this instance, I have cosine squared is going to equal 1 minus sine squared. So now I can replace this with cosine squared. Notice I haven't touched this yet, but look what just happened. I've got a cosine up here. I've got a cosine squared over here, but that's okay. I now have cosine in the numerators and my sines in the denominator. Anytime you have something that is multiplied, that's fair game. Cosine squared, the squared here in the middle, is the same thing as my trig function squared. So one of these cosines in the top takes out one of those in the bottom, and I still have one left over. And it just happened. Cosine, one of the cosines takes that out. I have 1 minus sine and cosines on the top. That is why it is so, so, so very important for you to have your identities memorized, because you want to be able to say, oh, no problem, I can do that. Oh, no problem, I can do that. And then work that through. Let's do another. Oh, that's right. I remember this one. Oh, this is so exciting. When I look at this problem, this piece right here, all of a sudden, I get to see this, and it is perfect square trinomial. This is a sine, that's alpha, right? The Greek letter. Sine squared alpha, 2 sine, and then this is the perfect square trinomial. I can break it up. Factoring doesn't go away, people. Learn it, love it, recognize it. All of you that keep trying to do that stinking quadratic formula to solve this stuff, quit. Factoring, factoring, factoring. Use your factoring. And then over here on this side, it's the same concept of what we did before, where I have that squared term. Now, if I have secant minus tangent, a lot of times it works if you try to get that denominator where it needs to be instead of the numerator, especially since I have a single term down here. So let's try it. I don't know. So if this is a minus, I can multiply it by secant plus tangent. Whatever you do to the bottom, you have to do to the top. Now secant alpha here plus tangent alpha, that's just the exact same thing, and I've got it squared. Here, I square the first term minus square the second term. Secant squared minus tangent squared is kind of my best day ever, because we now have it as a Pythagorean identity. And that's over 1. Check. So that takes out that denominator, which is awesome. Over here, I'm still digging on this. So this is where you look ahead. So now I'm looking ahead. If this is a 1, I've got secant theta plus tangent theta. What do you know about the denominator of secant? That's right, it's cosine. What do you know about the denominator of tangent? That's right, it's cosine. And that's what I'm talking about. That's exactly what I'm talking about. If you see your goal is over on the right, use this goal in order to see how this is going to play out. Well, what do you know about secant? Oh, it's 1 over cosine. What do you know about tangent? Oh, it's sine over cosine. And then that is going to be your next step. Sometimes you can't always see super far in advance, but in your head is what I'm talking about. Seeing in your head these next steps. That's when you get good at these. All right. It's just like factoring. The more factoring you do, the better you get at this. So now that I have a common denominator, I'm just going to put my numerator together and look at what's happening. Look how this is playing out. My goal over here, I have 1 plus sine. My goal over here is to have cosine. If you have a rational expression that is squared, you can square the top and square the bottom. And that's what I just did. And that's how this works out. All right. So I'm just talking through the notes this time. I actually worked them through whenever the voice was a lag on that. But I'm not going to go back through and record all of these because that's too much work. So look, I'm going to keep those posted, and we're going to go with these. And then hopefully this works out. And then just come with any questions that you have. You know I'm happy to help.